Static electricity is huge in AP Physics 2. It's one of the largest units in the entire study, and so it's most likely that you'll see one of these on the test. So let's get started. All right, first off, everybody, everything's made of atoms, protons, neutrons, and electrons. And some of these parts have charges and others do not. The neutron does not have a charge. So from here on out, we don't care about neutrons and static electricity because only things with charge exert a force on each other. So we're only interested in the proton part and the electron part of the atom. And here are their properties. Notice that the electron is much smaller in mass than the proton, but they have the identical size charge as each other. One's positive and one's negative. Now, this charge, this E charge, we call it the quanta of charge. That is the smallest size of charge that we will see in static electricity. Now, until you get up to high energy physics where you're smashing things together and breaking them into tiny parts, for normal matter, this is it. This is as small as it gets. So it's the building block of charge. Everything comes in a multiple of this quanta of charge. If you ever see a question where it's not a multiple of 1.6 times 10 to the negative 19th coulombs, then it can't be possible. All right, next thing, conservation of charge. Protons and electrons are real things. Since they exist, they have to not just vaporize. Actually, we'll talk more about that in modern physics. We can make them vaporize, but that's another discussion for another day. But the key thing is that the charge that we start with, Q, the initial charge, has to be the same as Q, the final charge. They don't just disappear. So the amount of net charge we begin with is the same as the amount of net charge we end with. This is one of the pillars of static electricity. Okay, opposite charges attract and like charges repel, which you should already know. Okay, how do objects get charged? Well, we have three methods: friction, conduction or contact, and induction. Let's talk about friction first. Different materials have a different pull on electrons, so when you put them together, some of the outer valence electrons will get stolen by one of them, and that leaves the one that stole the electron negative and the one that lost the electron positive. We learned about this in chemistry on the periodic table. An example of that would be a hair and a balloon. A balloon is a great object for stealing electrons. And so when you put balloon and hair in contact, the balloon steals the electrons, leaving the balloon with a net negative charge and your hair with a net positive charge. You can see that up here. Human hair is more likely to be positive, and our balloon is down here more likely to be negative. So anything up here that's on the positive side, put it in contact with anything down here lower, and this will become positive and this down here will become negative. Friction is just to give it a little extra energy so that they transfer the. Okay, conduction. The key thing is there must be physical contact. So I like to put down the word contact with conduction to remind you that there has to be a connection. Or otherwise, these physical things, protons and electrons, don't just magically jump. There has to be an electrical connection between the two. When we have contact, they share the charge. So the net charge will be distributed between the two objects. Only electrons move in a solid. So like, say we take this object which has a net negative charge, we touch it to a neutral object, electrons will flow over to the neutral object. But say we have a positive charged object. We like to say things, we pretend these positives move over, but technically they don't, because positives are protons trapped in the nucleus. So what really happens is some negative electrons over here move to the left, canceling out some of these positives, leaving this neutral object now positive. So it appears that positive charges move. Now we can say that, but in reality, it's the electrons that are moving in solids. All right, let's talk about induction. This is our hardest one. Okay, the key thing in induction is that the objects get close, but they do not touch. All right, so you bring this negatively charged object close to this neutral object. That's step one. And what happens is when you bring it close, this object polarizes. Now, polarize means that there's a positive side and negative side. That doesn't mean all the electrons flow to one side and all the protons flow to the other, but that there will be an excess of negative on one side, an excess of positive on the other side. Okay? This separation is temporary. If I take this away, then these charges will flow back to the way they were before. Okay, so they're forced to move and separate. Okay, so this object here is polarized. Now, if you ground this object, you provide an escape path. And so the deal is now we only had this single object polarized. Now we have a system that includes the object and the Earth that's polarized. So the Earth picks up the negatives, and the positives, the excess positives, stay on the object. So this too is temporary. If you take this charged object right here away, then these negatives will come back. So to complete the process of induction, you have to do one last thing. You have to disconnect the ground. Okay? If I disconnect this escape path, then what happens is these positives are trapped. These negatives can't come back on. And so induction is a way to charge something the opposite sign charge of what you have. So say this is negative. If I want to charge my hand negative, I just touch it by contact or conduction. But if I want to charge it positive, if this is negative, then I just bring it close and I go through the process of induction. And then I will force my hand to become positive. All right, a way that we test whether something has charge or not, since we cannot see the electrons or the protons, is we use a device called an electroscope, where they'll have a metal conductor here with something movable down at the bottom, like aluminum foil, and that'll be insulated from its surroundings. Another one, like the one we saw in class, was something more like this. We bring a charged rod near to it, and this charged rod here, if it just comes close, it will push positives up and negatives down. And so it'll polarize, and this little leaf will swing out because it's polarized. If I take this away, it's temporary, it'll go back to normal. If I want to make it permanent, I can touch this, and negatives will flow from the rod to the electroscope, causing the leaf to move out and stay. A charge insulating rod is brought near to, but does not touch a neutral conducting sphere, suspended from the ceiling by a thread. Okay? So, and here's what it looks like. A first question is, why does the sphere swing to the left? Well, this neutral object polarizes. And so what we end up with is a net charge on this side that's closer to the rod, that attracts, and the part that's repelled is farther away from the rod. So it gets less of a force of repulsion. Let me show you on a piece of paper. All right, so here is our sphere and the charged rod. Now I've just written down that the charged rod is positive, and the sphere swung to the left. Now, it swings to the left because of polarization. Now what happens is there's negative charges over here on the left that get attracted to the rod, leaving a positive side over here. Now, the negative and the positive attract, so you get an electric force here for this distance d. And over here on the right, you get a repulsion force, but this is quite a bit bigger distance. And so the electric force of repulsion is less than the electric force of attraction. So we end up with a net force, electric force to the left of attraction. Now, this is really important. So what happens is anything that can be polarized will be attracted to any charge at all. So a neutral object is attracted to anything. Now, so that makes this swing to the left. And if we touch them together, then we have contact or conduction. And what happens then is we share this net charge. I had 2, 4, 6, 8 over here. I have 4 of them moving over. I don't really know how many. And then what ends up happening is now they repel each other, and we have a net force of repulsion, and it swings back to the right. So it'll end up swinging to the right of vertical. Now let's see if we answered all of our questions. All right, so it says, why does the sphere swing to the left? Because it's polarized, there is a charge separation, and so there is a net attraction between the insulating rod and the neutral conducting sphere. What is the charge of the rod? Well, in my drawing I put down positive, but we really don't know. The rod could have been negative or positive. It would attract the neutral sphere either way. And C, if the sphere touches the rod, what will happen? Well, they'll share charge by contact. They'll have the same charge. And then D, the final position will be it'll swing away from the insulating rod because now they have the same charge. Conductors versus insulators. All right, remember that insulators, they cannot let charge move. Charge stays in place. So if I put a net charge on an insulator like this, it's going to stay put. It can't go anywhere. So it's stuck. And when you polarize them, an interesting thing happens. They actually polarize. They polarize on an atomic scale. So these are my little pictures of atoms here, so that they stay in their atomic structure, but the electrons spend more time on one side of the nucleus than the other. So you end up with a tiny net charge separation. So an insulator will still be polarized on an atomic scale. Now, conductors, on the other hand, the excess charge can go anywhere on the conductor, but since the excess charge will repel all the other excess charges, say like protons or positives on this conductor picture over here, then they'll all move to the outside surface. There will be no excess charge inside ever once it's in static equilibrium, because they will move all the way to the outside. And we'll talk more about that later, why that has to occur. Turns out it has to do with electric field and electric potential. Now, when you touch a charged object to a conductor, or you touch two conductors together that have excess charge, it's shared equally throughout the entire surfaces. All right, they share the charge entirely, not like an insulator. So like this is plastic, this is an insulator. So if I charge this up and I touched something with it, only the area that was touched will have a possibility of the charge moving over because it's an insulator. The rest of these won't move off. When you polarize a conductor, the entire device polarizes. So we have a much larger charge separation, and so the attraction between this conductor and this charge will be larger in general than the attraction between this insulator and this charge here, if the charge magnitudes here are the same. Conductors that are in contact act as one big object. If you're a tiny little electron moving around, and as long as the conductors are touching, then as far as you're an electron go, it's all one shape. So X, Y, and Z down here, if these are all conductors, that's all one object as far as charge goes. So here's our example. We have three conducting spheres on insulating stands. They're placed so that they're touching as shown. A negatively charged rod is brought close to Z over here. So here's a negatively charged rod is brought close. What is the charge of each of the spheres when they're in this position? And then B, the rod is held in place. X is moved away to the left. The rod is then moved away. And then finally, Y and Z are separated. What's the charge on each one? The spheres are all discharged and again placed as shown in the figure. The rod touches the sphere Z and is removed. What will be the charges of each sphere then? All right, I'd like for you to try to figure this out on your own first, and then I'll work it out with you. So here we are with our problem. We have this negative charged object brought close to these. Now, these are all conducting, so they're one object as far as the charges go. So it's going to polarize. Positives will be drawn to the right. I'm going to draw 1, 2, 3, 4 just to keep things simple. And I'll have 1, 2, 3, 4, an equivalent amount over here. Remember, we have conservation of charge. So this thing was neutral to begin with, has to be neutral at the end. Now, it says this X is pulled to the left. So it's stuck with 1, 2, 3, 4. They're trapped. And these positives are still over here, 1, 2, 3, 4. Now we take this away, and we have 1, 2, 3, 4 trapped on here. and we have 1, 2, 3, 4 that's spread out on these two because they're one object. And technically they should be on the outside surface. I'm just drawing them in this middle so we can see them. And then if we separate these, we'll end up with 1, 2, 3, 4, 1, 2, 1, 2. So if I call this negative q, this would be positive q over 2 and positive q over 2. So that if I add it up, the net charge is still the original 0. The last part of the problem asks what happens if we discharge all three of these, put them back in their original position, and then take this original rod and touch it, and then take these away, or take it away. So when it touches it, it's going to share some of its charge with this system. So some of these negatives will flow onto charge Z. And since they're all touching, they're going to spread out everywhere. And when we take this charged rod away, then they'll just spread out evenly throughout the entire thing. So they'll end up with a charge of, well, if the charge that transferred over was negative Q, then each one would have negative Q over 3 at the end because they're the same size. Now, if these were not the same size, the one that's bigger would end up with more of the net charge at the end. And we'll talk more about that in the video on electric potential. Here's our equation for electric force, K, Q1, Q2 over R squared. I have absolute value signs here. This is really important. Absolute value. Please just don't worry about the sign of the charge. Just worry about the direction of the force based on whether the charges attract or repel, and you'll know that by the signs of the charges. Because this is a radial geometry equation. And so it gets kind of confusing. It doesn't tell you left, right, up, or down with plus and minus. Look, our force is proportional to Q1, Q2, 2 charges. It only handles 2 charges at a time. So if you have more than 2, like we'll see in an example in a second, you'll have to find the force between them in pairs. And it's also proportional to 1 over r squared. So the radius makes more difference than the charge itself. K, or 1 over 4 pi epsilon naught, those of you that are in physics C will understand why it's this way, is just a constant. And don't worry about it, it's on your constant sheet. So let's take a look at some problems. Here's our first one. I have 3 conducting spheres that are charged as shown, each with a charge of either plus or minus Q. So this was a plus Q, and a minus Q. What's the direction of the net force on the leftmost charge? And derive an expression for the force on this leftmost charge. So I'd like for you to work that out, and then I'll do it with you. Okay, remember that our force is proportional to 1 over r squared. So these charges are all the same magnitude, but the force between these two will be larger because it has half the distance between these two. So I'm going to end up with an attraction between these two. I'll make this my blue force. And here's my green force. I'm going to have a much larger force over here to the left. So our net force will be to the left. Okay, so how big will this green force be? Well, F equals K, Q1, Q2 over R squared. And for us, that's going to be K, Q squared over D squared. And then our blue force over here will be K, Q squared again, but that's over 2D squared. So that's going to be 4D squared. Now this one's going to be to the right. I'm going to make that one positive. This one's going to be the left. I'm going to make that one negative. So my sum of my forces will be, this is like 4 over 4. So this is going to be negative 3/4 KQ squared over D squared. And we're done. So it's to the left. Question number 4, we have 2 conducting spheres. The one on the left has a charge of negative 6 coulombs, and the one on the right has a charge of plus 2 coulombs. The force between the 2 spheres is F. Okay, now the spheres are brought together in contact and then placed back in their original position. What's the new force between the 2 spheres? Okay, now this time remember that force, the electric force, is proportional to Q1 times Q2. So our original force will be because of these two charges, 6 coulombs and 2 coulombs, and they will attract each other. So I'll put that force here, call it F. All right, now what happens when we bring them together? When we bring them together, they become one object, they share the charge. The net charge right now is -6 plus 2, so -4. They're going to share that charge evenly. So this one's going to end up with a -2 coulombs. This one's going to end up with a -2 coulombs. That's what we end up with. So now they're going to repel each other. That's our final force here in orange, opposite. So what's happened to our charges? Well, this one has only changed sign. This one is now 1/3 of what it was before, but kept the same sign. So let's see. So this one has changed sign, but this one is 1/3 of the original. So what's our new force? -1/3 the original. So the force 2 will equal force number 1, but in the opposite direction, and 1/3 the original. All right, our final question for forces. We have a negative charge of -q placed at plus d 0, so that'd be right here. We already have a plus q charge up here and a plus q charge down here at plus d and minus d. Calculate the net force on this charge over here, and then the negative charge is moved to the origin. What's the new force on the charge? All right, I've color-coded this to make this a little easier for us to see. We have a -q charge right here. I made this one a green charge and a blue charge down here. So the green charge and this charge here are going to attract, so it'll be an attraction force up this way. The blue one will do the same thing down this way. Now, this is all symmetrical. Always look for symmetry when you're doing one of these problems to see if you can eliminate some of your effort. These two are going to add up, and the y component is going to disappear. So what we end up with is something like this. We're going to end up with a net force to the left. All right, so you guys remember this little triangle. If this side is d and this side is d, this side over here is d times the square root of 2. So that's going to be our radius. So when we solve this for the blue one, we end up with q squared over the square root of 2d, all that squared. So when we square the denominator, we get 2d squared. So this is the force for the blue one. Well, the green one's the same. They're going to add up to be horizontally to the left. And this right here is also a 45, 45, 90 triangle. So that means this force F, the final force to the left, will just be this times the square root of 2. So I get square root of 2 q squared over 2d squared, and we're done. The last part of our question asks, what happens if we move this -q to the origin? So if we put this here, -q, notice how it will be attracted up and attracted down. It's all symmetrical, so these two forces will cancel, so it won't do anything. It won't go up or down. It would stay in place if we leave it there. Now, if we happen to release the charge from here, it will shoot to the left because it'll accelerate to the left, but when it gets to the center, there's no force, so it will shoot to the farther to the left. It'll overshoot the origin. And when it gets over here, it's going to end up with a net force back. And that's simple harmonic motion. This thing will move back and forth and oscillate. All right, everybody, great job. We will see you in the next video when we start talking about electric field.